So we are doing more, divide, and conquer. So the aim of today's lecture, maybe the next lecture, would be to sort of highlight something about divide and conquer, which there's some sort of magic in divide and conquer, which is at some level you can understand dynamic programming, it makes sense. Greedy algorithms, sure, you can come up with a greedy algorithm. But in divide and conquer algorithms, and even now, even after doing this for so many years, there's an element of magic to them, that you can come up with results which are very surprising, that you wouldn't expect. And a lot of unexpected algorithms come from divide and conquer, and I want to give you a few examples of this. So I'm going to start with a fairly simple problem which is going to have a very clever algorithm, which is the problem of selecting order statistics. This is just a fancy word or a fancy phrase for given an array A of, let's just say, of numbers and an index k, output the kth largest element. Right? So, really simple problem. I give you an array, find the kth largest element of the array. Okay? So, if k is equal to 1, which is the largest element, then it's just trivial. Linear time, go and find the element. If k is n being the length of the array, then also it's simple. The nth largest element is the smallest element, which you can find. But what if you want to find, I don't know, the n over third largest element, or the median? So when k is equal to n over 2, this is find the median. So we just said when k is equal to 1 or n, this is easy. Linear time. Right? So for loop O of n operations. How do you find the median of an array? Of course you could sort the array. So you can find this in n log n. Right? Easy to do in n log n. Which is by sorting. So a natural question is finding the median easier, or is it significantly harder? Is it asymptotically going to be harder than finding the minimum? Or can we, we know that we can do it in n log n. Now obviously you need n, right? You have to actually just read the array. And so this is quite challenging if you really think about it. How are you going to find the median of the array without actually sorting it? Right, so I just want to pause and think about this question. How do you find the median? Yeah? But that's going to be n log n, because you're inserting into a heap is log n.
Well, you could, it's a slight optimization. The heap is of size, it would be of size k.
If it's of size k, you would keep inserting until?
Until it gets to a size, if the heap is of size k, then you can insert into the heap and also pop out of the heap like an element.
Right, but the thing is you still have to insert, so here's the heap, right? Your heap over here has size k. This has length n. So you're going to keep inserting one by one.
Right, until it's like size k.
Okay, so then at that point you've reached k elements.
Yes.
But then the kth largest element could be somewhere there.
Could be somewhere there, at which point you keep iterating, but at least the insert and the insert operation will be log k instead of log n.
Okay, good. So, but then how are you actually going to find that kth largest? At what point do you say, okay, I have the kth largest element?
Well, you could do like an entire like traversal doing those operations.
Okay.
At the very end, let's say you had its kth largest. I don't know if it's a, let me think, if it's a min heap or max heap. At the very end, the element should be at the top. But
At the very end, so if you look at the kth largest element, so you're going to keep inserting, and if it's a, so if it's a min heap,
min heap would work, right? Because you would have all the largest elements will be at the bottom of the heap, and you have the kth largest at the very top.
okay, I think, okay, that's a good solution. So you're saying you're going to maintain a heap of size k, you keep inserting elements one after the other. What you will do is, you'll always remove, so maybe you should technically make this k plus 1 elements. And then every time you remove the minimum, you know that that cannot be the kth largest element. Right? Because in any set of k plus 1 elements, the kth largest is never going to be the minimum. So you keep doing this, and as you keep extracting, you will never remove the kth largest element. When you finish, you will have the k largest elements in your heap. And indeed, the smallest one of those is the kth largest element. You could also just go ahead and sort that. So good. So that solution gives you n log k. Okay, that's good. So when k is small, you get something. But of course, when k is log n, oh, sorry, k is n. If I want the median, you're back to n log n.
Observation is k is at most n over 2, because when it is larger than n over 2,
You can swap, sure. Yeah, k is at most n over 2 is fine. But asymptotically, that's not making a difference. But okay, so this is good. So we can get O of n log k. O of n log k using a heap. Good. So indeed, this does more, right? You can actually get, you're doing more than what's necessary because you're getting all the kth largest elements. Indeed, you'll also get them in sorted order because the heap you could just sort with that. So good. Okay, so n log k using a heap. Good. I haven't written the solution, but okay, that's a start. Can you beat that? The thing is that anytime you're going to start using a heap, you're going to pay at least some log k. You're going to be processing each element. The question is, can you do O of n? Right? Indeed, the punchline is if you use divide and conquer, I'll give you an O of n algorithm to find the kth largest for any value of k.
So you need a constant time merge.
You're not going to use a data structure. You're going to use divide and conquer, right? So it's going to be very hard to break it up into that. You're not going to use a constant time merge on a heap. You're saying like use a meldable heap, like heaps that you can merge. The problem with any data structure of that form that you use is you're going to pay a log k or a log n somewhere for each operation. You have to sort of intuitively, whatever operations you're doing, you'll probably do it on all the elements. I mean, not guaranteed, but still. So first, I'm going to give you a solution that seems like it's cheating. And then I'll give you a solution. Well, anyway, I'll give you two solutions. So the first solution I'm going to give is going to demonstrate something more. I'm going to use randomization. So here's the idea, and I'll write out, pick a uniform at random index, or basically element from A. Right, so what this is saying is, here's your array. Just maybe I should let me just reorient laptop, maybe turn it a little bit this way. Okay, good. So pick something at random. Okay. Step 1. And let me refer to this element, call it x. So I just got some value x. Partition the A by x. So what does partition mean? Do you all recall what partition means? It means you basically move all the elements less than x to one side and all the elements more than x to the other side. Right? So this has been done in quicksort. There's linear time one can do this. So what happens when you do partition? So you end up with x over here, everything less than x over there, and let's just say everything greater than or equal to x over here. Right? Partition by x to get 3. Well, technically it's just 2 sets, but I'll just say it's 3 sets, sort of, I'll call it the A less than x, x, and the A greater than or equal to x. Right? That subscript simply means you're looking at all the things that are less than or greater than or equal to. Okay, so now what? If you think quicksort, so now how would you do divide and conquer? I've done the divide. You want the kth largest element. Yeah?
You already know which one has to be based on the number of elements, right? Like, if there's more than k elements in the bigger than x set, then it's going to be there.
Exactly. So, or rather what you so equivalently what you say is, suppose this is R, right? Sorry, let me refer to this just for convenience as R minus 1. And this is n minus R. This is n minus R.
Professor?
Yeah?
I'm not able to see what you
Okay, all right, sorry. Yeah, just please call out if you can't see. Okay, so R minus 1, n minus R. So now you have 3 cases, right? So I'll just say 3. A is if R is equal to K. Sorry, I'm doing K at smallest here instead of K at largest. So allow me that change. Let me do K at smallest as opposed to K at largest. Right? So K at smallest. So if R is equal to K, then you just output X. You're done.
Wait, isn't that the k largest?
This would be the Kth smallest, right? Because these are the small elements.
Aren't there k elements smaller than the k largest? Oh,
I guess, okay, am I doing an off by 1? I mean,
yeah, it's the k small.
it's the K at small. Like I'm okay, it's annoying, right? I'm actually saying the first smallest instead of the 0th small. The first smallest is the smallest, the second smallest is, but the index is off by 1 in that case, the array index. Anyway. So if R is less than K, well then you output, okay, so now you have to do this randomly over here. So I'm referring to this part as A less than X and this array as A greater than or equal to X, right? So what do you output? So I don't know, I'll refer to this as select. I'll call this the select algorithm. So you output the select algorithm with A less than X with K again. Wait a second. What am I? I'm mixing everything up here. Sorry, I'm making mistakes in my index. So if r is less than k, then actually the kth largest is going to kth smallest is going to be here, not there. Okay, so sorry. Let me fix this. If r is greater than k, right? So this portion is actually larger than k. Then you output select a less than k, a less than x of k. Right? You get the kth largest in here. If r is less than k, then it's over here, but then you have to shift it by, you'll do output select a greater than equal to x of k minus r, because you remove the first r elements, right? It's the k minus rth element in this portion, right? So this is my randomized select algorithm. Does this make sense? Now, we haven't gone through any theory of randomized algorithms. Like, what does it even mean to have the running time? You have to start defining these things. Because depending on what you choose at random in the first step, it's going to affect the running time of the algorithm. So technically what you look at is the average runtime. But be careful, it's not the average over all inputs. It's the average over the randomness for a fixed input. So I will write this down, but I want you to think, when you say average, it is not the average over a random input. You think of, for every input, you look at the average runtime and you look at the worst average. That's what average case, that's what average means in this context. So I'll write this down. But any questions about the algorithm? It's quite simple, right? I mean, if you've seen quicksort, it's basically just quicksort. Pick a random index, partition, and then you just have to go to one part. If you were so lucky that this was always a half-half split, then things look like it would be good. Except you don't know, right? I mean, it's random. Okay, so let me, now that we have this algorithm here, let's actually do, so the running time of a randomized algorithm. So let me define it as follows, right? So the running time for A. How many of you have heard of the term expectation? Okay, so a few of you. So let me not use that term. Let me just say I can look at the average runtime of A, which is saying what? The average running time, where the average is over the randomness of the algorithm. The average running time over the randomness of the algorithm. Average running time for the input A. So you're fixing an input. Normally when you have an algorithm, if you fix the input, the output is always the same. But in a randomized algorithm, depending on the randomness of the input, the running time could be different. The output is always going to be the same because it's always correct. But depending on what happens here, if it makes some really bad choices, suppose it partitions in the worst way possible, then it might just end up being a linear time algorithm. But if it partitions it in a really nice way, then it might be much faster. Not linear, actually even worse. Sorry, quadratic time algorithm. Sorry, quadratic. If it partitions in the worst way possible, it could take n squared time, because it would basically pick something at random, partition. What if r was always 1? Was so unlucky to always pick the minimum element to partition, it's going to run in n squared time. But if it was so lucky as to always pick x in the middle, well, it seems like it'll do much better. So this is the average running time on A. What is T of n? This is like the worst case runtime. Is basically the maximum average runtime of A for all A of length n, which is your usual notion of worst case runtime. So this is the worst case running time for this algorithm select. This is, again, I mean, it's only 3 lines, but it's very important that you understand this. There's a quantification order here which is important. Because normally when you have an algorithm, there's only one parameter, which is the input. A deterministic algorithm has the input. For any input, the behavior is the same. Now there are 2 things involved. There's the input and the randomness. So what you do is, for an input, you average the randomness, then you take the maximum. You are not averaging over all inputs, which also is sensible. Like there's something called the average case analysis, which has meaning in various places. But that's not what we're doing. We are averaging over the randomness of the algorithm. So imagine the experiment is, I fix my array, and I just run this over and over again. I say, what is the average runtime that I get? And I say, what is the worst this could be over all possible inputs? Is this clear? You will also get the same, because we'll show that it's linear time, right? So yeah, the average randomizing over the input is not going to make a difference, because in effect the randomization of the choice is going to basically get rid of that. But in general, that could have an effect. In this case, you're right that it does not. Okay, all right. So let's try to understand what T of n looks like. Okay? So I'm going to go back to this and write out the running time here. So this step is just O of 1, just picking at random. This step here is linear, O of n. Now the problem is with this. Like, we don't know exactly what this is going to be. But let me parameterize this as the following. I can certainly argue that in the worst case, the algorithm is going to have to search over the larger one. So it's only making one recursive call, not 2, right? It's making one recursive call, either to the left or to the right, almost like binary search. One recursive call, but we don't know the size. So I'm just going to upper bound this by saying the running time here is the max of r minus 1 and n minus r. Is that clear? So I'm just going to write down that recurrence here, that T of n is at most T of the max of r minus 1 and n minus r plus O of n. And what is r? R is the index of the random element, the index of the random element in sorted order. Right? Precisely, r is the position of that element. Again, sorry, numbering my indices I'm numbering my arrays from 1 and not 0. So apologies for that. This is really annoying when you switch between math notation and CS notation, and then you have these off by 1 errors and whatever. But you understand what R is. R is the index. So you pick a random element. R is the index of where that would end up if you actually sorted the array. Yeah?
What if there's like a bunch of elements that are the same, so there's no like, you don't necessarily know which index it is?
So what you could do is assume that you break ties depending on the initial index so that you have an explicit sorted order.
Okay.
Right? So you could, I would, in general say that assume that the, I see what you mean. Yeah, let's just assume that we have a tie-breaking rule amongst the elements. I mean, in general, if you were a little careful, what you would do is you could break this up into 3 blocks where you had all the elements equal to x in the middle, because in linear time you could collect those, and then you could then just decide on which of those blocks to run on. And if it's the one in the middle, then you know the answer. So the worst case is really when all the elements are distinct. So let me just stop that annoying ding-dong sound. Yeah, okay. There. Okay. So far so good? Yeah.
Why is the math not given?
Because you're looking at the worst case.
Oh,
You don't know which one it's going to be, so I'm just assuming that it's actually the worst. The worst is you're in the bigger one. The minimum would be the best case, but we want a worst case bound. So this is an upper bound. Right, so this is an upper bound. Now, how do we solve this recurrence? Because we don't know what R is. But surely we have a distribution on R. So what is, we can write this out as an average. So this max, the max of R minus 1 and n minus R, I'll say lies in the range n over 2 to n minus 1. Right, because one of the halves is always going to be at least, one of the parts is always going to be at least a half. Okay? If you pick the minimum or the maximum, your size is n minus 1. If you pick the second minimum or the second maximum, your size is n minus 2. If you pick the third minimum or the third maximum, your size will be n minus 3. So on and so forth. Right? So essentially what this says is, if the algorithm picks index R or n minus R, then this max value will essentially be the same, right, regardless of which one it is. So I'll just say that for R less than n over 2, this thing is essentially going to be n minus R. Does that make sense? The larger half, if it picks the rth smallest or the rth largest, which is the index R n minus R, or picks element at sorted index R n minus R. So this is saying that in this array, there's one way. So let's go back to this picture. There is exactly one way in which this one is going to be of size R minus 1, the part to the left, which is if it picked the rth one. And there's exactly one way in which the part to the right could be of size R minus 1, which is if it picked the rth largest. In both of those cases, it's n minus R, assuming R is less than n over 2. Okay? So we sort of know the distribution. Now, what is the probability of picking this or this? What is the probability of picking these choices? 1 over n for each of them, so 2 over n, right? The probability of picking that index is 1 over n. The probability of picking the other one is 1 over n. So this is with probability. The probability is equal to 2 over n, because there are exactly two choices, this choice and this choice. So if you average, what you get is t of n is at most, okay, let me write something and then you ask me if there's any confusion. Probably 2 over n, t of n over 2, plus t of n over 2 plus 1, plus t of n over 2 plus 2, plus t of n minus 1, plus O of n. I was saying is that with probability 2 over n, you get a running time of t of n minus 1. With probability 2 over n, you get a running time of probability n minus 2. With probability 2 over n, you get n minus 3, so on and so forth. What are the two choices? So again, assuming that n is even, there are exactly two choices to get n over 2, which is the middle two elements. If you pick any one of them, then the other part is of size n over 2. Right? So with probability 2 over n, you get each of these choices. So you're averaging over all these choices. This is expectation. I'm just computing the expectation, but if you've heard that term. But this is the average. Does this make sense? Right? Averaging over all of these runtimes. So with probability, it's n minus r, which implies it's basically going to be t of n minus r in these cases. So r is ranging essentially from 1 to n over 2. This is a very sort of strange expression. Your master theorem doesn't seem to help you all that much over here, right? This is exactly why you need to have some idea of, so how are you going to deal with this? So in the end, unfortunately, I'm just going to use induction. I'm going to guess the right answer and plug it in. But now how are you going to guess the right answer? Okay, so any questions about this expression? Is this clear? So far so good? Right, so for such a simple algorithm, we have to do all this work. Okay, so now let's kind of think about this expression here. What is the average size that you get over here? 3n over 4, roughly. Right? So on the average, the size of the larger part is 3n over 4. Right? Because this is averaging n over 2 plus 1 up to n minus 1. Ignore the off by 1 errors. Right? 3n over 4. Suppose that's what I got every time. Let's just do a back of the envelope. This is how you guess the solution. This is not a proof. I'm going to guess a solution basically using a heuristic argument. I will verify that that guess is correct by doing induction. So the induction will be the proof. But this is the guess. This is an unfortunate part of a lot of the way research is done, is if you read a research paper, they won't tell you how they got the guess. They'll just say, the solution is this, prove it by induction, and that's the proof. But the way that they get it is by making these hand-wavy arguments, trying to solve the recurrence using those hand-wavy arguments, using the recursion tree, and then going back and checking whether that works. Okay, so what we know is the average size of the max of the larger portion, which is n minus r. So the average is basically 3n over 4. So, and you can think of this as basically just computing some average. It's a weighted average because you're doing 1 divided by n over 2. And there are n over 2 choices here. Right? So another way of writing this is to divide that by n over 2. So this is basically looking at the average runtime. I'm cheating. I'm saying look at the average size and take that runtime. right? I'm cheating here when I'm looking at this. So I'm just saying if I did this, I'm going to guess that T of n is at most, I'm guessing this. This is making a fallacious argument. It's saying that the average T is T of the average, which is not true. Actually, there's a whole theory of when this is true, and that happens when this is like, when it's a concave function and various things like that.
Like it's only true when the function is linear.
Also, when it's concave, it'll be an upper bound. When it's linear, it's an equality. This is known as Jensen's inequality, right? So when T is a concave function, then actually you will also get that to be an upper bound. When it's a convex function, it won't be the case. But yeah, what we're going to show is that, so here's the funny thing. We will show that T is linear. Hence, this is true, although we didn't assume that it was true to get here. But we make these leaps of faith. Sometimes it doesn't work. But in this case, it works exactly for that reason, because linear functions satisfy Jensen's inequality, and so things work. Anyway. Okay, so let me recap where we are. So T of n I'm just going to move this here. We said T of n is equal to T of n over 2 plus T of n over 2 plus 1 plus T of n minus 1 divided by n over 2 plus O of n. Yes, less than. We guess that T of n is at most T of 3n over 4 plus O of n. Let's just solve this recurrence. The solution of this recurrence will give us our guess. We will go back and check that this guess is true by induction. Okay, so now let me do our usual, let me construct the recursion tree. So this is at most, so think of this as C times n, right? This is at most C times n. How many recursive calls? One recursive call, 3n over 4. At most, what is this going to be? 3 over 4 Cn. 3c over 4 times n. What goes in here? (916). 3 over 4 squared. Right? So it's 3 over 4 squared n. This is going to be at most 3 over 4 Cn. Do you see the pattern? What's happening is that the total work is decaying exponentially. So this is the third type of recurrence. Last time, in merge sort, all of these are equal. In that improvement for the stock market problem, they were exponentially increasing. And here, it is exponentially decreasing. So the total work is equal to the sum of I going from 0 up to log base what? Log base 4/3 of n. Right? Because that's how many levels you need to go down, because it's decaying. So log base, okay, sorry, I'm going to write this out somewhere else. Total work, summation, I going from 0, log base 4/3 of n of 3 over 4 to the power I Cn. But what did I tell you about the sums of geometric progressions? When it's decaying, it's dominated by the first term. When it's increasing, it's dominated by the last term. Again, you can apply your formula here. You can apply and check the formula if you want. But you can see that because it's decaying, it's basically a geometric series which will converge. Right? In other words, I could just say this is at most C of n I going from 0 all the way to infinity of 3 over 4 to the power I. This is a convergent series. Actually, the sum is basically convergent. Right? This is just a geometric progression. It's, you know exactly, what is the formula for this? Doesn't even know what this thing is? So it has a very nice, simple formula. How much is this? This thing is 4. Its value is 4. The formula on the blackboard, it's basically the formula on the blackboard, except, and well, you have to change the index here. And 1 minus 2, this is, I don't know what that is. Okay. It's essentially something like that, right? This is 1 divided by 1 minus 3 over 4, which is equal to 4. So when you have a recurrence of this form, this implies that T of n is O of n. So linear. So our guess is it's linear. Again, all this work thus far has only been there to make a guess. It is not a formal proof. We've only guessed that it's going to be O of n. And now we'll just use induction, and it's going to pop out that it will actually be O of n. Because going back to your comment, because the function is linear, you can replace the average of the function by the function on the average, and so it works out. If actually this had not been linear, if it had been quadratic, then that argument would fail, and actually it wouldn't go through then. Any questions about this? Yeah, so we did these. Let's pause here. Let's go back to the beginning so that we can see the bigger picture, right? Okay, what is the bigger picture? We said, okay, look, we're going to use this randomized approach for selecting the kth largest element. We pick a random x in the array, we partition, and then we decided to go to one half or the other. Now what we're trying to do is a worst case running time analysis. So we'll say in the worst case, the algorithm always had to look in the larger part. Might even be better sometimes. Maybe sometimes it looks at the smaller part. But suppose it always had to look at the larger part. The running time would then be t of the max of r minus 1 and n minus r. It's the max of those larger portions. And the rest of the work is just O of n because it has to partition. Okay? So, with that, we go back and we say, okay, what is the probability that the larger portion had size n minus r, where r is something between 1 and n over 2? So the probability that it got exactly n minus 1, for example, would be the probability that that random step picked the smallest or the largest. But that happens with probability 2 over n. 1 over n for the smallest, 1 over n for the largest. So with probability 2 over n, essentially for every r with probability 2 over n, the running time is t of n minus r. So we average over all those choices. It's like saying with probability 2 over n, it's t of n over 2, which is the best case. If we were so lucky as to pick the middle two elements, then we get the best split. If we were so unlucky as to get the worst, you get t of n minus 1. If you always got t of n minus 1 here, you'd get quadratic. If you always got n over 2, you get linear. So it's some average between these. And you might say, why is the average of a linear and a quadratic term linear? Well, I mean, this is in some sense the magic of divide and conquer. Lots of things that seem like it shouldn't happen start happening. Because technically this is a linear function. When you average, it's like, think of it as the probability of doing really bad is really low. But the probability of doing reasonably well is quite high. Because even if you get to within 3/4 or 5/6, or even a 99% versus 1% split, you're still removing some fraction of the input each time. And so it starts decaying. So there are many other ways of analyzing this. Indeed, the whole field of analysis of these things is called the analysis of randomized algorithms. That's sort of what I work on. And there are multiple ways of analyzing this. One thing you can try to do is you can try to track the size of this as it goes down. Sometimes it's going to shrink, sometimes it's going to stay, then it's going to shrink. And you can say, how long is it going to take for this thing to shrink all the way? It's another way of looking at the analysis. All of these, so there are multiple ways of looking at this. I think that, if you're unfamiliar with a lot of that, the easiest way to think about it is to write the recurrence in this form. Now, to make a guess for this recurrence, we're saying, okay, let us just guess that we always get the average size. That the call, we're going to say the average of the t's is t of the average. The running time of the average runtime is the running time of the average size, which is incorrect, but we'll make this as a guess. And we guess that t of n is at most t of 3n over 4 plus O of n. Solve this recurrence using, or rather, guess this recurrence using our favorite recursion tree. You get that the answer is O of n. Now to sort of complete the argument, we have to say, let's go and verify that O of n is correct by induction. Okay, so now what I'm going to do is I'm going to state a theorem. Suppose t of n is at most 2 over n summation t of n over 2 plus I goes from 0 up to n over 2 minus 1 plus c of n, and t of 1 is at most c. Then t of n is O of n. And this turns out to be, once you know the right guess, it's actually a fairly simple argument. It's about 3 or 4 lines. Okay, so we prove by induction. By induction, we prove that t of n is at most c prime n. C prime will be chosen later. You'll actually see that the choice of c being 4 times c is going to work. And that 4 is the same 4 that came from there, effectively. But anyway, so base case, the base case, n is equal to 1. So t of 1 is at most c, which is at most c prime 1. We're done. Okay, now let me do the induction on a separate page. So for the induction, so we get, remember, t of n is at most 2 over n summation I going from 0 to n over 2 minus 1, t of n over 2 plus I plus c of n.
The plus I is exactly.
Oh, I'm sorry. Yes. Okay? So by the induction hypothesis, t of n over 2 plus I is at most c prime n over 2 plus I for I strictly less than n over 2. Right? Because then it's basically, you could think of this as strong induction, because you're assuming it for everything up to that point. Okay? So far so good? So now let's just plug and play. Let's do our usual. So T of n is at most 2 over n, summation I going from 0 to n over 2 minus 1 of C prime n over 2 plus I plus Cn. Okay, so I'm just going to move some things around over here. I get 2C prime divided by n. The C prime comes out. Summation I going from 0 to n over 2 minus 1 of n over 2 plus I plus C times n. This is the sum of an arithmetic series. N over 2, n over 2 plus 1, n over 2 plus 2, all the way up to n minus 1. This is the sum of the arithmetic series. There's a formula for that again. It's basically the number of terms times the average of the first and the last. Or if you want, you could basically you could break this up into two summations. The first summation is trivial. It's n over 2 squared. And the second summation is the summation of I going from 0 to n over 2 minus I of I. You can solve this in any number of ways, right? But what is this? So again, it's like you're summing. If you want a picture, what are you summing? N over 2, n over 2 plus 1, n over 2 plus 2, all the way up to n minus 1, right? So if you sum this and this, it is the same as the second term and the next term, so on and so forth. It's another way of looking at it. Or if you want this part is a rectangle and this part is a triangle, then you use area, whatever. Like you could do this in many different ways. So we get 2C prime over n. How many terms are there in the series? There are n over 2 terms in the series. What is the first term? The first term is n over 2. The second term is n minus 1. We're taking the average of those two things. Remember what we said. We start with C prime n. We have to be able to get C prime n over here. We can't get C prime plus something. It has to be C prime. So at this point, with all these calculations, it's still not clear that everything is going to check out to our advantage. Yeah, go on.
You mean the last term, right? So n over 2 is the first term and n minus 1 is the last term. That's how you take the sum of an arithmetic series.
Yeah.
I think you said second term.
I'm sorry. So first term and last term. Sorry. Yeah, first term and last term. Okay? Okay, so far so good. All right, so let's like now crank this out now. Okay, 2C prime over n times n over 2. So that's this n over 2 will clearly cancel. And then the next thing we'll see is you'll get 3n minus 2 divided by 2. Right? I'm just saying that's 2 times n minus 1, so 3. This thing plus C of n. Here's your 3n over 4 kind of in this thing. If you really wanted to see where the 3n over 4 is coming from, it's the 3n divided by 4. Like if you ignore this, then you get something that looks like 3n over 4, which is exactly the average size. Because you're taking the average of the runtimes, but the runtimes are linear. And when it's linear, it's the average of the size. It's like saying if you average a linear function, it's just the linear function on the average value. That averages 3n over 4 with some lower order change. There's the minus 2 which you can ignore, which is lower order with respect to this. Okay? All right, so Let me make sure I'm doing this right. I've made a mistake here. I'm not sure where the mistake is. Because this is not going, okay, so let
3n minus, it should be
3n over 4, sorry.
Sorry, over
There it
4.
is, there it is, yeah, that's what I thought. There's the 3n over 4. Oh, okay, now it works. Sorry? Yeah, this is minus 2.
Minus 2.
Minus 2. Yeah, okay, good. So 3n over 4, sorry. Yeah, okay, so good. So now there's the 3n over 4. Okay, so this n cancels out, the 2 cancels out. What do you get? You get c prime times 3n minus 2 divided by 4 plus cn. What is important is it's c prime times something less than 1. So we can set c prime to be sufficiently large compared to c so that this whole thing is going to be less than c prime n. You're going to have to go back and maybe look at this carefully. Some of you are nodding.
Can't you just substitute for c? Like c is equal to c prime over 4?
C prime times 4, exactly.
No, I mean small c, like normal c is equal to c prime over 4.
Sure, but then that's doing it the opposite way because c has been fixed by the recurrence. You have to choose c prime.
No, I'm saying if we choose c prime as 4 to c,
Then we're done, exactly.
then you just like replace your 3n over, like you get an extra n over 4, right? That's what we want. Right?
Yeah, but instead of thinking of replacing c as a function of c prime, you should think of the other operation. You're choosing c prime as a function of c because you want, c is what is fixed by the recurrence, and c prime is what your proof is choosing.
Sure.
So if c prime is basically chosen to be 4 times c, because we can choose that because our proof, we want to prove that t of n is less than c prime n, and we will choose that c prime as long as we choose it to be a constant. And we'll choose it to be 4 times c. So if you choose c prime to be 4 times c, well then observe that, oh, that's what you mean by c prime over 4. Okay, I think I understand now. You get 3 c prime n over 4 minus whatever, c prime over 2 plus c prime n over 4, which is at most c prime n. And so that completes the proof. Okay? If nothing else, what you have learned is that selecting the median can be done in linear time using randomization. So it's not a bad time to take a break. So stretch your legs. If you could get caffeine in 2 minutes, get some caffeine in 2 minutes, because what we are going to do after this is going to bend your mind even more, like than this. This was the easy part of today's lecture. We are now going to do the really interesting part. Any questions from the remote audience? Or if there's some other part of the notes that you would like to see, then let me know. Maybe I can zoom out and yeah, go ahead.
Back to the algorithm.
I'm sorry, which?
algorithm.
This one?
Like how to do this. Not this one.
That one.
This one.
That one.
Use the firstly, if R is equal to judges R equal to K. If for the first time I do not get the answer I want, so I will do this way, like a circle.
It's recursive.
Okay.
It's this procedure is just calling itself recursively.
Okay.
Yeah. I actually wasn't planning on doing this until like about an hour ago or a couple of hours ago that I thought maybe I should do this. If you actually come to my office, you'll see this calculation like quickly scribbled out on my whiteboard, just to make sure that it all works out. But I think it's a very illuminating thing to see. Like, okay, maybe a lot of this doesn't make sense yet, but you go back, it'll make sense. But it's very illuminating to see how divide and conquer works for this problem. This is surprisingly not as well known a fact as you might think, that you can find the k at large, you can find the median in linear time.
And also the partition doesn't mean we'll make the smaller one in order.
No,
Just smaller.
just smaller. Yep, exactly. Yeah. So partition is really just to find all the elements less than it and more than it. And usually there's a way of doing it with 2 pointers. If you read about quicksort, you can do it with 2 pointers. You can just do a scan of the array and copy things separately if you want to. But there's a way of doing it without using extra memory.
So the rough time is O and is N.
For the partition, yeah. It's just one scan over the array. It's not at all a complicated algorithm. It's actually quite simple. I'm curious, actually, do any of you watch the videos of the lectures? Yes? Do you use the one on UJA? Or do you just look at the one on YouTube?
Oh, I didn't know it's uploaded on Media as well.
Oh, it is, yeah. Okay, well. So then you're not a useful person to answer my question. I was going to ask you whether one was better than the other or not, but they're both fine? Okay. I think it's automatically uploaded.
No, we cannot see it.
You don't see it?
No, I see it.
Really?
I always see the recording on YouTube. From the web page, you just.
Yeah, but so the UJA ones are not available to you? Oh man, that's.
The YouTube ones are there.
They're there, right? Yeah, maybe there's some other place to look, because from what I understood, so when I record over Zoom, then that is not automatically put up. I have to go somewhere and click to say share this. But these lecture captures are done automatically. That's what I was told. And when I check, it says that it's shared, and there are two feeds, right? There's one feed of the camera and one feed of the projection system. Yeah. No, it should be there. I don't know what the student page looks like, so I don't know where exactly to click. But if you can't find it, like post on Piazza or something, and someone, I'm sure, will answer.
For the Tuesday lecture, if you just log out for the Zoom, so I'm wondering if there have some recording existing.
Of that last part at the end,
Yeah.
that will not be there, unfortunately, because the recording stops promptly at 1:15. Because I'm not handling it, like it's done class times. So. Okay, all right, so what is the punchline? The punchline is that you can find the kth largest element or the kth smallest element of an array in linear time using randomization. So a natural question that people asked is, what if you're not allowed to use randomization? Can you still do it? And so the answer is you can do it, but now the algorithm is completely mind-bending. Again, it's not complicated, but it's well, I don't know. You look at the algorithm, and usually there's this sense of like, how on earth did they come up with this one? Okay, so it's deterministic, linear time selection. Okay, so deterministic linear time selection, same problem. So what's the idea? The idea is you want to get something that looks like this. Right? That's the recurrence you want to get. You'd like to make one recursive call, to an array that's smaller. Even instead of 3n over 4, if you get 1 minus delta n for constant delta between 0 and 1. If you can get any constant, it will still, you'll get it. Essentially what you want is an exponential decrease in your array each time. Right? Because as long as you can shrink it by some constant factor, it will keep shrinking, and then essentially all the math will check out. The only way delta affects everything is by the constant. So here is like a really crazy divide and conquer procedure. So here's what you're going to do. So you're going to take your array, and we're going to break it up into chunks of 5. Okay, that's easy enough. Break it up into chunks of 5. Sort each of them, and then sort. So you sort, so on and so forth. So remember, like if you could find the median of the array, then of course you'd be done. I mean, done as in you could then partition. You would partition the right way. As long as you can find an element that has a reasonable rank, you could partition. So you're trying to find the right element to partition with. Except, you want to do this in linear time. So here's what you do. So you take the median of each group of 5. So you could sort this, and then you look at the middle element of each of these. Right? You look at the middle element of each group of 5, which you can find in linear time. So I'll say, this is really step 2. Step 1 is break into groups of 5. second step is take the median of each group of 5 to get the array. I'm just going to call it A prime, right? So A prime is the array of medians. Now what you do is recursively compute the median of A prime. You're using divide and conquer, so just recursively compute it. That element becomes your x. Okay? So you recursively compute the median. Call it x. Partition by x. Right, so you partition by x. And then, step 5 is, you have the sort of A, B, and C, partition by x, let the rank be R. The rank is like the index in the sorted order, and if R is equal to K, if R is greater than K, if R is less than K, you do whatever has to be done, right? There's some recursive call that's made here, right? So then you just output select of A less than X of K, otherwise you output select A greater than or equal to X of K minus R. Why is this complicated? Well, you're doing 2 recursive calls here. Right, so this is doing select A prime of, technically the rank would be something like n over 10, because it's the median of n over 5 elements. So you have one select call, one recursive call done here, and one recursive call done over here. Either this or this. So definitely your recurrence does not look like that. It has 2 recursive calls. So now it's not so clear that things are going to check out anymore.
The first recursive call is contained inside the function, so you can analyze the first recursive call and give it the upper bound and analyze the whole thing.
Well, I mean, you can do it all together with, we'll write a recurrence. We just need to argue that recurrence is going to be in linear time. I mean, it's a little hard to analyze this separate of the other calls, because, I mean, it's all done in one. The recursive one now has both calls, and you have to, right? You can't just look at that call making its own call. Yeah, that you could analyze. That's easy. What you're saying is you could look at the recursive median call, which is going to do a recursive median call, so on and so forth. That part is easy, but then they're also forking off all these other calls to the selection procedure. The first thing we need to understand is, why is this a good element to partition with? Why is this a good element to partition with? Sorry? It's not exactly half, right? Because it's the median of the medians. So it's not the median.
It guarantees it's between the 1/5 position and the 4/5 position.
Almost, yeah. So it guarantees you something.
So it's more than just constant from the end or the start.
It's bounded away from, yeah. So it's essentially some other value of delta. But the problem is, you have to make this extra recursive call, and you don't know if the sum of those two things is going to sort of work out. The 5 was chosen a little carefully. It's not just random. I think if you do it with 3, you could do it with 3. The math is not going to work. So let's see. Okay, so first, let's ask. Okay, so anyway, does the algorithm make sense? So it should be clear to you that the algorithm is correct. Forget the running time. It's correct simply because it's just partitioning by some element. So it's using the same idea in the randomized version. It's partitioning by something. Okay, so let's first prove a claim here that the rank of x, x is this median of medians. The rank of x is in 3n over 10 and 7n over 10. Okay? Okay, so why? So here's a picture that will help you think about this. So in each of these you sorted. So this element is bigger than both of these elements. And this element is bigger than both of these elements. This is bigger than both of these elements. So if x is bigger than the middle element, it's going to be bigger than 3 elements in that block. So anytime x is bigger than one of these shaded elements, it's bigger than 3 elements in that block. And x is the median of the shaded elements. There are n over 5 shaded elements. X is bigger than n over 10 of them. So it's going to be bigger than 3n over 10 elements overall. I'll write this down. But that's the 3n over 10. And it's also going to be less than 3n over 10 elements by the same logic. So its rank is between 3n over 10 and 7n over 10. Okay? So x is the median of A prime, the shaded elements. Hence, x is at least, or I should say x is greater than or equal. Let's assume that all elements are distinct, right? Just let's assume that everything is distinct just to get rid of corner cases. So we'll just assume it's greater than. So x is greater than n over 10 elements of A prime, right? Because the size of A prime is n over 5. So it's greater than n over 5. So there are n over 5 elements. It's greater than at least half of them. It's the median. So it's greater than n over 10 elements of A prime. Every time you're greater than one of those elements, you're actually greater than 3 elements of the block. Right? So I'll say if x is at least the median of a, I think I call it a group, it is greater than 3 elements of the group. Right? So x is at least the median. I'll say is greater than the median of n over 10 groups. Hence, x is greater than 3n over 10 elements. Okay? Similarly, x is less than 3n over 10 elements. Same argument, right? You just sort of reverse greater than and less than, because it's the median, all the arguments will check out. So the rank of x is in 3n over 10 and n minus 3n over 10, which is 7n over 10. Okay? So this seems like it's a reasonable split to make. So when we do the partition, we know that both of those are at most 7n over 10. So let us now go and look at the running time of our algorithm. First, linear time. Second, linear time. Third step is t of n over 5, because you have to compute the median of n over 5 things. Fourth, O of n. The last step is at most t of 7n over 10. Yeah?
I'm still confused about why it's larger than 3.
Which is larger than 3?
Unlike the rank of R is, not this one. For the next page, yeah. Why is x is a median of a prime and it will be larger than 3? Because the group is have five.
It has 5 elements.
Yeah.
So the median is greater than equal to itself.
Oh,
Yeah, maybe I should be is greater than. So this is greater than equal to itself and 2 elements, but the median is x is going to be greater than it strictly. So I should have been more careful about that. Right? So it's greater than the median, which means it's greater than that element and greater than those others. Yeah. Okay, so there's one called Tn over 5 and the second call is T of 7n over 10. And everything else is linear, so the recurrence is T of n is at most T of n over 5 plus T of 7n over 10 plus O of n. So here's the magic. What is 1/5 plus 7/10? How much is that? 9/10, which is less than 1. And so the thing is linear. Okay, so it's a magic of the constant. If you actually chose it groups of 3, it won't work out. I think groups of 7, it will work out. Like when you make the groups larger, it works out. But with 5, it works. Okay? So now that is brilliant. That was genius. It's actually, in practice, is not a very good algorithm. In practice, you could just do the randomized one. In practice, actually, the randomized one is much better. But they showed that you could still do it deterministically. Okay, so I'm just going to quickly work that math out for the recurrence so that we can see it work out. We have 8 minutes before the system stops recording, so let's do this quickly. So again, I'll just write this out. Tn is t of n over 5 plus t of 7n over 10 plus c of n. T of 1 is at most c. Okay, so we prove by induction that t of n is at most c prime n. We will choose the c prime shortly. I think maybe it'll be like 10 times c or something like that. And so base case is t of 1 is at most c, which we'll say is at most c prime. We'll choose c prime larger. The induction as we'll say t of n is at most t of n over 5 plus t of 7n over 10 plus c of n. And so by strong induction, t of n over 5 is at most c prime n over 5, and t of 7n over 10 is at most c prime times 7 n over 10. Okay, now I'm going to sort of just plug all of these things in, which is t of n is at most c prime n over 5 plus 7 c prime n over 10 plus cn. And now you'll see everything work out. So this is n times 9 c prime over 10 plus c. So if you set c prime is equal to 10 times c, then you get that this is equal to c prime over 10. 9c prime over 10 plus c prime over 10 is equal to c prime n. And that completes the proof. So this is like really magical divide and conquer here, right? And what is especially surprising about this is that the recursive algorithm is used twice in two different ways, right? So the first time it's actually used to find how to partition, and the second time, the second call is the more conventional call. It's actually just doing a divide and conquer step, right? Kind of like binary search or whatever. But the first step that it actually uses it recursively, and there is some magic in the constants working out. Because 7/10 plus 1/5 is strictly smaller than 1, that's why the math works. Try it out for 3, and you'll see that it fails. So if you have 3 groups of 3, then every time you're more than the median, you're more than 2/3 of the points. Right? Write down the recurrence, and you'll see that you cannot prove it by induction. Actually, it's not going to be linear. Because this call is just too large. It's going to be working over n over 3 points, which is a lot. Okay? So, but with 5, it works. And indeed, if you increase it to 7, I think it will still work. Because the more you increase it, this call becomes sort of smaller and smaller. Sort of in the limit, as the blocks become larger, you're getting closer and closer to the actual median. Okay? Any questions? Any questions about this or anything we've done so far? So again, the whole topic for today ended up being selecting the kth smallest element, basically selecting an element based on rank. And what we argued was that you can do it in linear time. There's a much more simpler procedure which is randomized, although the recurrence that it leads to is more complicated, or it was more complicated to analyze because it's not the typical kind of recurrence that you see. But I think in terms of the just generally the principle behind the algorithm is much easier to understand. I think if you don't understand the randomized, then the deterministic starts being even more surprising. But you understand the principle behind this algorithm is you want to get an even split, and that way your search time will reduce exponentially. It starts decaying rapidly. So with randomization, it's sort of easy to find a good split. Easy meaning you just pick one at random. You just have to argue that it works. To get it deterministically, you have to use the algorithm itself recursively. And the algorithm ends up being cleverer and trickier to come up with, but the analysis is actually easy because the recurrence that you get is quite simple. And you can just analyze it directly. Okay, so this is a good point to end. And also because there are only 2 minutes left. I don't want to start anything with 2 minutes left. When we come back on Tuesday, we'll do more surprising divide and conquer algorithms. So what is this? This is what, week 7, right? 8, 9, 10. So we'll do one more lecture on divide and conquer. I wasn't exactly sure what to do after that. I typically don't like to teach on the last lecture. I usually leave it open for questions. Just open for any questions that you may have about anything. At least anything that I can talk about. So, you can ask. I think the only rule that I have is no religion and no politics, because I don't want to use this as a soapbox. But I'm happy to answer any other questions that you have about me, about what I work on, about the job market, about. I can opine on the status of many different things indefinitely. So the last lecture I leave open. I'd like to have 2 lectures. I think that NP completeness is